We're now going to look at calculating the TAS in a different way. This time we're looking at the total air temperature and the Mach number. When we fly at a constant Mach number, the percentage of the speed of sound is constant. Temperature doesn't affect the actual Mach number, but it does affect the speed. As we identified earlier, at high temperatures TAS is faster, at low temperatures the TAS is slower. But the Mach number doesn't change, it's not affected by temperature. In the Boeing 727 and similar aircraft, the pilot does not have an outside air temperature, but instead will have a total air temperature, as we mentioned some time ago. So we need the total air temperature to calculate the TAS while in flight. By comparison, if we are planning a flight, we don't have the total air temperature, we simply have a forecast outside air temperature. TAT calculations on the CR computers use the indicated temperature window, which is this little section here and here. We can see is basically identical on both types. Just the Mach number on the Jeppesen is above this little arrow, whereas on the APRs it's above this little indicator here on the outer scale. Think of this window as the TAT and Mach number window. We're going to use the sliding cursor in this type of calculation as well. Let's look at the components of the indicated temperature and Mach number window on the CR-3, which is virtually identical to the APR. We have some wiggly lines here which are at 10-degree intervals, so 0 degrees C, minus 10 degrees, minus 20, and so forth, and in a positive direction, same sort of thing, at 10-degree increments. This is the total air temperature in degrees Celsius. There is also a spiraling line which we're going to be using here, and that varies according to our speed. There's a TAS scale down here representing our true airspeed, and down the bottom here we have the rise in temperature that corresponds to this particular Mach number. So in this case we've got Mach 0.78, and we can identify the temperature rise when we use the cursor down in this window. The Mach number is also identified. Just remember, the APR gives us a more accurate Mach number compared to the Jeppesen. We have the same sort of scales, the only difference is the Mach number is on the outside rather than being somewhere in this vicinity. Let's now look at the recovery coefficient cursor. The cursor on the Jeppesen has two lines with a coefficient of 0.8 or a coefficient of 1. The APR on the other hand has three of these, and the third one curves back here with a recovery coefficient of 0.6. The straight line represents the recovery coefficient of 0.8. The curved line represents the recovery coefficient of 1.0. The Boeing 727 has a total air temperature, so the recovery coefficient is 1, so we're going to be using this curved line. You'll notice that there are two curves. The dashed line is to be used at sea level, whereas the solid line is to be used in the stratosphere. We only ever use the solid line. Let's look at an example where we're given the calibrated airspeed, the flight level, and the total air temperature. So this is an in-flight calculation. An aircraft is cruising with 300 knots at flight level 290. We have a TAT of minus 22. Find the true airspeed. So the first thing we have to do is to align the calibrated airspeed, which is in this window here, 300 knots, against the pressure altitude of 290. So let's rotate the inner scale until we match up. We now have flight level 290, remember the numbers are going in the opposite direction, flight level 290 against 300 knots. We get our Mach number down here above the arrow. On the Jeppesen it would be somewhere underneath this indicated temperature window. And so we have a Mach number of 0.775. On the Jeppesen, here we have the Mach number identified, 0.775. Now that the navigation computer is set up, we now need to get to the intersection of the actual TAT of -22 where it intersects with this black line. So we're looking for -22, which is going to be in between these two curved lines and where it intersects on that reference line. So there it is there. So we're now going to rotate the cursor around with a recovery coefficient of 1 and place that over the top of that point of intersection. So -22 on the curved line, and we come down and we read our true airspeed underneath that, 450 knots. If you wanted to, you now look at this little arrow here and you can see that there's a temperature rise of 27 degrees. That would allow us, if we wanted to calculate the still air outside air temperature by subtracting that from our TAT of -22. And so we can calculate it, -22, take off the 27 resulting from the temperature rise. That means the still air temperature would be -49 degrees Celsius. On the Jeppesen, we get the same sort of result. Here are some exercises for you to try. Once again, pause the video now so that you can do your calculation, then resume to see what the correct answer is for each exercise.